Welcome to our deep dive, you guys, into the fabric of the cosmos.
Oh yeah, The Fabric of the Cosmos by physicist Brian Greene.
Yeah, exactly.
We're taking a journey
It's going to be a wild one.
into the mind-bending world of space and time and reality.
Greene's book is remarkable because he takes these incredibly complex ideas
Right.
about the universe and makes them understandable.
Makes them understandable, yeah.
Yeah.
You really don't need a scientific background to grasp
I think that's what's so cool about
the
it.
core concepts.
Yeah, it's true. He uses metaphors and analogies so brilliantly.
Huh?
It's like he's handing you a new pair of glasses and you can see the universe in a whole new light. I admit I still had a few, wait, what, moments reading it.
Yeah.
That's why I'm so glad you're here with me, to help unpack some of these intriguing ideas.
I'm happy to dive in.
Yeah.
One thing that struck me about the book is that it's not just about understanding the universe, on a grand scale.
Right.
It also challenges our perceptions of reality itself,
Mm-hmm.
which has huge implications for how we see ourselves and our place in the cosmos.
There's that anecdote early on
Yeah.
where Greene talks about encountering Kama's book and that whole question about
Right.
whether life is worth living.
It really gets you thinking.
Yeah.
It really got me thinking.
It's interesting because Kama seems to suggest that understanding the universe doesn't really change that fundamental question.
Right.
But Greene takes a different stance. He argues that if we want to understand the meaning of life, we need to understand the universe in which life exists.
It's like he's saying, hey, if we were a species that only experienced the world through touch, wouldn't the discovery of sight and hearing
Right.
completely change our understanding of life?
He uses this great analogy of humans living in a cavern,
Okay.
experiencing the world only through touch. So imagine them suddenly discovering sight and hearing.
Wow.
Yeah.
And the world outside the cave.
Yeah.
Their entire perspective would shift.
Right.
Greene believes that understanding the universe can have a similar effect on our understanding of life itself.
Yeah, it makes you realize how much our limited perspective
Totally.
shapes our reality. Speaking of shifting perspectives,
Yeah.
I was particularly fascinated by the debate between Newton and Leibniz
Oh, yeah?
about the nature of space.
This is where things start to get really interesting.
Mm.
Newton believed in absolute space. Space for him existed independently of objects. Think of it as a giant empty container.
Okay.
Yeah.
Leibniz had a completely different take on it, didn't he?
He did.
He saw space as relational. It was simply a way of describing the positions of objects
Uh-huh.
relative to one another.
Right. To illustrate this idea,
Okay.
Leibniz uses the analogy of the alphabet.
Hmm.
So the alphabet provides order to letters,
Uh-huh.
but without the letters themselves, it has no meaning.
Okay.
Similarly, for Leibniz, space only has meaning in relation to the objects within it.
So if you removed all the stars, planets, and everything else, space itself would cease to exist.
That's the essence of Leibniz's argument.
Wow.
This debate about the nature of space has profound implications for how we understand motion and gravity. It even influenced Einstein's thinking. In fact, there's a concept called Mach's principle, which suggests that inertia, an object's resistance to change in motion, is a result of the gravitational interaction with all the matter in the universe.
So our experience of inertia, like that feeling of being pushed back in your seat
Uh-huh.
when you accelerate, is somehow connected to the distant stars and galaxies?
It's a radical idea.
Hmm.
Einstein himself was deeply intrigued by Mach's principle, and it played a role in his development of general relativity.
Whoa.
This brings us to the relativity revolution,
Right.
which completely upended our understanding of space and time. Einstein showed that these concepts are not absolute, as Newton believed, but interwoven and relative to the observer.
Wait, so you're telling me that time isn't this universal ticking clock?
Nope.
That's the same for everyone.
That's right. One of the core ideas of special relativity is time dilation.
Yeah.
The faster you move through space, the slower time passes for you relative to someone who's stationary.
That's wild. I remember reading about the Hopfield-Keating experiment,
Oh, yeah.
where they flew atomic clocks around the world on a plane.
Right.
And when they compared those clocks to ones on the ground, there was a tiny difference
Crazy.
in the time that they had measured.
It's incredible, isn't it? We often think of time as this absolute unchanging thing, but experiments like that
Yeah.
show us how flexible it really is. The Hopfield-Keating experiment provided concrete evidence for time dilation and confirmed that it's not just a theoretical concept.
So let me get this straight. My now
Uh,
can actually be different from your now.
Exactly. Imagine space-time as a loaf of bread.
Okay.
Each slice represents space at a moment in time from a particular observer's perspective. If another observer is moving relative to the first, Their slice of space-time will be at a different angle.
I love that analogy. It helps me visualize how now can be relative. It's like everyone is slicing the space-time loaf differently based on their motion.
Exactly.
Okay, cool.
And this brings us to general relativity, where Einstein extends special relativity to include gravity.
Okay.
Now, gravity isn't a force acting across space, but a curvature of space-time itself.
It's like that classic analogy of a bowling ball on a rubber sheet.
Yes,
The bowling ball represents a massive object, and the dent it creates in the sheet represents the curvature of space-time, which we experience as gravity.
precisely. Massive objects like planets and stars actually warp the fabric of space-time around them.
Okay.
And this warping dictates how other objects move in their vicinity.
It's amazing how this seemingly outlandish idea
Yeah.
has been proven by real-world observations and experiments.
It's true.
For example, general relativity correctly predicted the bending of starlight around the sun.
That's right. And this is just the tip of the iceberg. We haven't even touched on quantum mechanics yet.
Oh boy, things are about to get even weirder, aren't they? I'm ready for more curveballs from the universe.
Get ready, because the quantum realm is unlike anything we experience in our everyday lives. One of the most mind-boggling concepts is superposition. It's the idea that particles can exist in multiple states or possibilities at the same time.
Hold on, are we saying a particle can be in two places at once?
It's not simply that we don't know where a particle is, it's that it genuinely exists in this blurry, indeterminate state. It's only when we measure it that it collapses into a single definite state.
So until we look at it, a particle could be spinning up and down simultaneously. Could you give me an example to help wrap my head around this?
Greene uses a brilliant analogy with a titanium box. Imagine a box with 3 doors inside is one of those alien spheres we talked about earlier, the ones that always flash the same color, even when separated.
Oh, right, the ones that baffled Einstein because they seemed to defy the speed of light they were entangled, weren't they?
Exactly. So you have 2 of these boxes, each with a sphere inside, and you separate them by a vast distance when you open one door on the first box and the sphere flashes red. You instantly know that if you open the corresponding door on the other box, its sphere will also flash red.
But how is that even possible? They're so far apart, it's like they're communicating faster than light.
That's the mind-blowing mystery of quantum entanglement. It's as if the 2 spheres are connected, despite the distance defying our intuitive understanding of space and time.
No wonder Einstein called this spooky action at a distance. It seems like something out of science fiction.
He wasn't a fan of the idea at all. Einstein believed it implied that quantum mechanics was incomplete. But what's remarkable is that experiments have actually confirmed entanglement. It's not just a theoretical quirk, it's a fundamental aspect of reality.
That's incredible. It's like the universe is playing by a completely different set of rules than we're used to. And what about the arrow of time? Why does time seem to flow in only one direction from past to future?
This is another question that has puzzled physicists and philosophers for centuries. We take for granted that time moves forward. But explaining why it has this direction is a complex challenge. One key concept in understanding the arrow of time is entropy.
Entropy, that's a measure of disorder, right? Like my desk always seems to be moving towards a state of maximum entropy.
Exactly. The idea is that systems tend to become more disordered over time. Imagine taking a perfectly ordered deck of cards and shuffling it. The chances of it ending up back in its original order are astronomically small.
So disorder is simply more probable than order.
That's the gist of it. Now think about the early universe. It's believed to have been in a state of incredibly low entropy, highly ordered time. This low entropy is thought to be crucial for explaining the arrow of time. As the universe expands and evolves, it naturally moves towards higher entropy, creating the directionality we experience as the flow of time.
So the arrow of time is essentially a consequence of the universe's tendency to move from order to disorder.
That's a simplified way to put it. Of course, there's a lot we still don't fully understand about time, entropy, and their relationship, but that's the basic idea.
I'm starting to realize that the more we learn about the universe, the more mysterious it becomes. And now I'm really curious about string theory, which I understand aims to be a theory of everything. That's a pretty ambitious goal.
It is. Physicists have been searching for a theory that can unify all the forces of nature. Gravity, electromagnetism, and the strong and weak nuclear forces within a single, elegant framework.
And string theory is a contender for this elusive theory of everything.
It's one of the leading candidates. And it's a pretty radical idea. Instead of point-like particles being the fundamental building blocks of the universe, string theory proposes that tiny vibrating strings are the fundamental entities.
So instead of imagining an electron as a tiny ball, we should think of it as a tiny vibrating string.
Precisely, the idea is that different vibrational patterns of these strings correspond to all the different particles and forces we observe. Imagine a guitar string vibrating at different frequencies to produce different notes in string theory. It's the same concept, but applied to the fundamental building blocks of reality.
That's a really elegant way to think about it. But I've heard that string theory is incredibly difficult to test experimentally.
That's one of the biggest challenges. Strings are thought to be so incredibly small, much smaller than anything we can currently observe directly.
So if we can't see them, how can we even know if they exist?
That's the million-dollar question. There are some indirect ways to test string theory. One is to look for evidence of extraspatial dimensions, which the theory predicts.
Wait a minute, extra dimensions, you mean beyond the 3 dimensions of space we experience?
You've got string theory suggests that there could be additional spatial dimensions curled up so small that we can't perceive them directly.
So our 3-dimensional world is just a slice of a much larger multidimensional reality. It's like we're those people in the cave unaware of the vast world beyond.
That's a great way to connect those ideas. Now, you might be wondering how we could ever detect these extra dimensions if they're so tiny. One way is through their potential influence on gravity. If extra dimensions exist, they could affect the strength of gravity at very short distances.
And what about those microscopic black holes we discussed earlier? Could they be a gateway to understanding extra dimensions?
That's another fascinating possibility. If gravity is stronger at short distances because of extra dimensions, it might be possible to create tiny black holes in particle accelerators, like the Large Hadron Collider.
Creating black holes in a lab sounds terrifying. Wouldn't they suck up everything around them?
Don't worry, these hypothetical black holes would be incredibly small and would evaporate almost instantly. They'd be more like little pops of energy than monstrous cosmic vacuum cleaners.
So even those tiny pops of energy could provide valuable clues about the nature of gravity and the existence of extra dimensions. This is all pretty mind-blowing. We've journeyed from the vastness of the expanding universe down to the subatomic realm of strings, extra dimensions, and even the possibility of creating black holes in a lab. It's like reality is more flexible and stranger than we could have ever imagined.
Absolutely, and we've only scratched the surface.
Yeah.
There's so much more to explore in this universe of ours.
Speaking of exploring further, I'm intrigued by this concept you mentioned earlier, the holographic principle. Does this have anything to do with those 3D images we used to see on credit cards?
Yeah, it all comes back to that puzzle of black hole entropy.
Right.
Remember how we talked about it being proportional to the black hole's surface area
Yeah.
rather than its volume?
Yeah, that's a pretty strange concept.
It is.
So you're saying the holographic principle can help explain why a black hole's information content is linked to its surface area.
Exactly. It's as though everything that falls into a black hole isn't actually lost. Instead, the information gets encoded on the event horizon, the boundary of the black hole.
It's like the event horizon acts as a giant cosmic hard drive,
Uh-huh.
storing all the information about what the black hole has swallowed.
That's a great way to visualize it. It's a truly mind-boggling idea that raises profound questions about the nature of information and reality itself. If the universe is holographic, it means that what we perceive as 3-dimensional reality might be a projection of information encoded on a distant 2-dimensional surface.
Whoa, that's a lot to wrap my head around. We've gone from the vast expanse of the cosmos to the incredibly tiny world of strings and quantum mechanics, and now we're questioning the very nature of reality itself.
That's the beauty of exploring these big ideas. The fabric of the cosmos doesn't just provide answers.
Right.
It sparks a sense of wonder and opens our minds to new possibilities.
You're absolutely right. Greene does a phenomenal job of guiding us through these complex concepts while keeping us engaged and curious. One thing that particularly fascinated me was his suggestion that we might one day be able to manipulate space-time to travel through time. Is time travel a genuine possibility, or is it destined to remain in the realm of science fiction?
Well, while the laws of physics as we currently understand them don't strictly rule out time travel, the practical challenges are enormous. We would need to figure out how to create wormholes, harness exotic forms of matter and energy, and find a way to navigate the thorny paradoxes that time travel presents.
So it sounds like building a time machine might be a bit beyond our current capabilities.
I'd say so, but who knows what the future holds? For now, the possibility of time travel remains a tantalizing mystery, a playground for our imaginations.
This deep dive has certainly left me with a sense of awe and wonder. I find myself pondering questions like, if time is an illusion, what does it mean to experience the present moment? Or, if the universe is a hologram, where does reality truly reside? These are the kind of questions that keep me up at night.
And that's a fantastic thing. Greene's book doesn't just provide information, it inspires us to question, to explore, and to appreciate the beauty and mystery of the universe. It reminds us that the more we learn, the more we realize how much we don't know. And that's part of the excitement of scientific discovery.
Well said. I think that's a perfect note to end on. Thank you so much for joining me on this incredible journey through the fabric of the cosmos. It's been a truly enlightening and thought-provoking experience.
The pleasure was all mine. I hope our listeners have enjoyed the ride as well.
And to everyone listening, remember to keep looking up at the stars, keep asking those big questions, and never stop exploring the universe, both within and around you. Until next time, keep those minds curious.